Okay, so here's where we are going to pick up today. So we're going to talk about Green's theorem some more. So getting started. Let's see here. So Green's theorem does have, surprisingly, some relationships to the fundamental theorem of line integrals and other related notions like path independence and gradients and stuff like that. And first, let me just point out why that's a little bit surprising. Right? I mean, they're in completely different contexts. Green's theorem is about a two-dimensional thing with a one-dimensional boundary. The fundamental theorem of line integrals is about one-dimensional curves with zero-dimensional boundary points. It seems like, okay, we know that there's analogs and we're kind of using a lot of the same ideas, a lot of the same strategies, but they seem like they're in totally different contexts. Okay, so I think it's surprising that there is a relationship. Here's how easy it is to see that relationship. So let's consider a solid region, as I have drawn here. And it's going to have a boundary curve around the outside. And let's break up that boundary curve by, here, I'll choose darker points, having a point there and a point here. And I'm going to break up that boundary curve by having one piece of it go that direction. I'm going to call that C1. And now seemingly wrong, or seemingly kind of backwards, I'm going to have the other part of that boundary go that way. Now, is that the same way, or is that the opposite way? Is a rhetorical question. And it's kind of both in different ways. Right? So the first answer I want to give you to, are these two curves as I have them drawn here, C1 and C2, are they going the same way or the opposite way? The first answer is neither. They're not the same curve. You can't compare the directions. And I think that's an important point of view. So, for example, this curve and that curve. Are they going the same direction or the opposite direction? I don't know what you're talking about. See what I'm saying? Right? So let's not get too worried about the question of whether C1 and C2 are going the same direction or opposite directions. The main answer is neither. The question doesn't make sense. Okay, that said, let's answer the question. So, in a way, C1 and C2 are kind of going the same direction, because check it out, they have the same boundary. In other words, they both start at the same point, and they both end at the same point, right? So in terms of how their boundaries compare, they're kind of in some sense going the same direction. Okay. All right, but so here's the thing. In terms of how they are part of the boundary of this initial region D, they're kind of going opposite directions, right? So you might say, for example, that C1 is going counterclockwise and thus the positive direction around the boundary. But C2 is, wait a second, it's not going counterclockwise. Counterclockwise would be, let's see, let me finish counterclockwise would be like that, which C2 isn't doing. C2 awkwardly is going clockwise, which is the negative direction around, thought of as part of the boundary of D. Right? So, it's interesting how there's that little contrast there. Be aware of how it is that there is a seeming sort of contradiction. It's not a contradiction, right? But it's got that vibe of paradox. Some people might call it a paradox. It's not actually a paradox, but there's an inconsistency. Let's call it that, right? And this is an intrinsic fact of geometry. Geometry is weird. It's just how it works. If you're going the same direction in terms of how boundaries relate, then you're going opposite direction in terms of how you're the boundary of the thing that you bound. Okay. Some people would like to fix this by orienting C2 the other direction. Let's do it that way. Now this is a plus, just like that is a plus. And isn't that nice? Well, the problem, of course, is that now we would have a minus here. The boundary of C1 and the boundary of C2 are no longer the same. C1 starts at the point where C2 ends, and vice versa. So there's nothing you can do. You can kind of shuffle it around, but you're going to have a minus sign in this picture, no matter how you do it. Okay, so like I say, that minus sign is intrinsic to geometry, and it makes more sense, I think, to do it this way. Okay. All right, so with this context set up, let's write down Green's theorem. Right? Suppose there's some vector field. We can write down how Green's theorem applies. Green's theorem says that the double integral over the interior of Green's operator is the line integral around the boundary. And don't forget that line integral around the boundary is like this. Specifically, Green's theorem refers to boundaries. Oriented as boundaries are oriented. Not the boundary curves oriented however arbitrarily you may have previously chosen and would prefer to think of them. Right? That's not what Green's theorem says. You orient boundaries this way. Right? So, given that we're going that way, I mean that means that C1 is going in the positive direction, but C2 we're going backwards. We're going the wrong way, and thus we get that minus sign right there. Okay, so this is what Green's theorem says. How are we doing? Is everybody on board? Right. Okay. Okay, so it turns out this equation is extremely powerful in allowing us to draw some conclusions. So let's play a little game here. Let's ask what happens if Green's operator is equal to 0 just from this equation. Well, if Green's operator is equal to 0, by which I mean identically 0 everywhere, right? Then, okay, well then there's a 0. Well, that means that this double integral is 0. That means that this difference, because that's an equal sign, this difference is also 0. If that difference is 0, wait a second, let's think this through. If the difference is 0, that means that no matter what 2 points I pick, the two different curves by which I can get from one point to the other point give me the same line integral. That's what path independent means. And of course we already know, we talked about this before, path independent is simultaneous with being a gradient. Right? So what I love about this little argument is let me zoom out one notch so we can see the thing. What this does is it gives us a kind of a geometric sense for why the boundary theorems that we've talked about in the past, not the lifetime theorems that we're talking about in the past are true. So let me flip back to that page. Where is it? Oh, come on, that's further back than I thought it was going to be. Here we go. So we talked before without any justification. I made this assertion that, if you compute Green's operator, if you get 0, then that means that there is an anti-gradient for that vector field. Right? And this was just trust me, it's magic, right? And now we have not only a sense for why that's true, but a geometric sense in some sense, certain point of view. Gosh, that's far back. Here we go. A geometric sense for why that really kind of should be true. Right? Green's operator being 0 means that you're a gradient of something because of this picture and what Green's theorem tells us. It's a slick argument. I think this is a powerful idea. I want to encourage you all to digest this. There's a lot of great intuition to be had from thinking about this construction and this argument. And now let me point out it goes the other way as well. If you have a function that's a gradient, well, if it's a gradient, it's path independent. If it's path independent, these two line integrals are the same. If those two line integrals are the same, this difference is 0. If the difference is 0, that means the double integral is 0. Thank you, Green's theorem. If the double integral is 0, now hold on, wait a second. The double integral is 0. No matter what points, no matter what paths, that means this double integral is 0 no matter what two-dimensional domain I pick. How could the double integral of a function always be 0 no matter what domain you pick? Well, only if the integrand itself is 0. And so there's a sort of a geometric point of view, again, kind of going the other way in the lifetime theorem as well. Now this one is arguably you don't really need this argument here because if f is a gradient, you could write down a formula. You could just straight up compute Green's operator. It's not hard to see that you get 0. But that is an algebraic argument. There's something a little unsatisfying about algebra in the sense that it tells you with a lot of confidence that something is true, but maybe not so much satisfaction on why it should be true. And I feel like there's more satisfaction in why this should be true by thinking about this picture and these observations in Green's theorem. So I'm a fan. Okay. Alrighty. Next thing we're going to do, this is going to seem like a change of subject, and it kind of is, but we're going to define a new thing called flux. Y'all may or may not have heard of this term before. If you have, cool. If you haven't, don't worry about it. But I want to give you some sense for what flux is before we go through and talk about how to compute it. Or I should say, I want to give you some sense for what flux represents physically. Right? So the first example I'm going to show you is, suppose we have a curve. And we're going to look at a little piece of that curve. We're going to focus our attention just on that little piece. And maybe this is a property line or like a fence or a border of some sort. And what if I've got a fluid of some sort that's moving across there? So now there's lots of things that this fluid could be. Maybe this is, maybe it's a fluid of pollution that's moving across some national border. Obviously, you want to be able to keep track of that kind of thing. Maybe it's a vector field representing how birds are migrating, right? Or wildebeest, what have you, right? And they have a direction, and they're moving at a certain speed. You might want to factor in, the density of, how many birds per square foot, whatever. Okay. So if this represents a fluid of some sort, reasonable question we might want to ask: whatever stuff this fluid represents, how much stuff per unit time is actually crossing that curve? Stuff per unit time. It's very natural, physically, right? So how many birds per day are flying across my border? How many kilograms per year of pollution are you sending across your border into our country, or are we sending across our border into your country, whatever? Okay, so natural questions to want to ask. So that's the big idea, and it's pretty easy to write down a formula that does this. The big idea is if you have a fluid flowing and you're interested in this thing called flux, namely stuff per unit time, to whatever extent the fluid is flowing parallel to the curve, I don't really care. That's not helping it go across, right? If the birds are just flying right along the border, okay, yeah, but the ones that are on our side of the line stay on our side of the line. The ones that are on their side of the line stay on their side of the line. It doesn't contribute to moving across. So all we really care about then, in fact, is just the part of the vector field representing the fluid flow that's in the direction of the normal vector, namely the part that's perpendicular to the surface, to the curve. Okay. All right. And that component, the bigger that component, the more flux you get. I think that's a pretty easy pitch. More perpendicular component, more flux. Analogously, I guess maybe why don't I leave that there. Analogously, the length of the curve. Bigger curve, more stuff. Right, again, I think that's a pretty easy pitch. Yeah? So this is the big idea. We're going to define this to be flux. Stuff per unit time of the fluid of the vector field going across that surface. And again, these are the components, the elements that go into defining that object. Okay. And then, of course, don't forget, we have a handy-dandy formula for components. Components are dot products, and specifically want the component in the normal direction, indirect. So F dot in is that component. Okay. So if I then have that, okay, so that's the flux across this little piece of curve. If I would like to know what's the total flux across the entire, some entire curve, whatever that entire curve is, well, then just add up over that entire curve. Right? And so here's our formula that we're going to use for a flux through a curve. So line integral f dot n ds. Now, problem, how do we compute that? Right? We don't have pre-existing formulas. Here's what we do know. We know how to compute, if we were to come across integral f dot, let me just use something different. Let me use g. Integral of g dot t ds. Here we're good, because that's just integral g dx. G dot dx, right? So we have existing formulas for how to compute integral something dot t ds, but something dot n ds, that's not we don't have existing, we don't know how to deal, that's not a thing that we can work with. Okay. So the way we can jump across that little impediment is as follows. It's a really clever argument, and that is to notice that let's suppose you have a piece of curve. Piece of curve here, and let's think of that curve as being part of the boundary of let's say this region over here. Right? And let's with that piece of curve, we can talk about the normal vector. Oh, okay. We'll use right, and if we have some F, some vector field representing the fluid we're interested in. So we're interested in this dot product, F dot n. That's what we want to compute the dot product of. If you were to just take this picture and just rotate the whole picture 90 degrees counterclockwise, let's just say, right? Notice that your unit vector perpendicular to the curve becomes unit vector parallel to the curve. It becomes our unit tangent vector t. Right? If you take that orange vector and rotate it counterclockwise, you get, well, something different. I mean, there's the formula for it, right? If you take p comma q and rotate counterclockwise, you get negative q comma p. That's an old chapter 12 reference. Note that this thing f and this thing I'm calling f rotated have the same magnitude and their dot product 0, right? So easy little trick there, chapter 12 trick. And so now I can just make the convenient argument that, well, okay, if you're interested in, I kind of run out of colors, didn't I? Here, okay, I'll use this color. If you're interested in f dot n, as we are, no problem. This rotation of f dot t, same thing. And that, again, that t is easier to deal with. It's easier to do integrals of stuff dot t because that connects up to our existing formulas. Okay, so that's the big clever idea. And now let's think about, with that trick in mind, let's think about the flux of some fluid through this boundary. Now, for example, birds, right? Maybe this is a flow of birds. Maybe this is a flow of pollution, whatever, right? This vector field represents any of many different things. And maybe we want to know grand total. How's the total population of birds in our little region here changing? I mean, to some extent, birds are leaving the region by crossing the northern boundary, but to some extent, they're entering the region. Right? So altogether, I mean, and I think the following appeal is reasonable, the rate of change of the amount of birds is just going to be the grand total of, you keep track across each little piece of border. To what extent are birds exiting? To what extent are birds entering? You add up all those things, and that's going to tell you how the rate of change of birds is on your interior. Right? And, I mean, other than the possibility that somebody's spontaneously generating birds somewhere, right? which, by the way, yeah, birds get born, birds die, right? So there's that too, right? But if we ignore all of that, then the flux around the boundary could be argued to tell us the rate of change of the quantity on the inside. I think it's a pretty natural appeal there. And we'll talk about the spontaneous generation and that kind of thing at a later date. So here we go. We're keeping track across each little piece of the curve. We're looking at the total amount of the flux on each little piece. We're then looking at the total around the entire boundary of that region. We have the formula from the previous page of how to compute flux, F.NDS, right? That was easy. That was our definition construction. From the previous page, we argued that F.N is the same as a rotation of F.T. We have that handy formula for the rotation. The rotation of the vector field, P comma Q, is negative Q comma P. Don't forget, going back to a couple of sections back, TDS is the dx vector that we're comfortably familiar with, right? And lo and behold, we have ourselves a line integral, and it's a line integral we know how to compute. Look, something dot dx, right? We're all good on computing this thing. So that's really nice. Okay. Another thing we can do with this construction is we know theorems about it. So we know the fundamental theorem of line integrals, and we know Green's theorem. Right? So let's write down Green's theorem as it applies, and this is a tricky bit here. It's tempting to say a line integral around a boundary is a double integral of Green's operator, and isn't Green's operator dq dx minus dp dy, isn't that the formula, right? But remember, that's the Green's operator applied to p comma q. This is not p comma q. Right? So really, Green's operator, when we say dq dx, we really mean the derivative of the second component with respect to x, and then minus the derivative of the first component with respect to y. So that's Green's operator as it applies to this adjusted, vector field that we had to rotate it, right, in order to deal with that whole in versus t thing. So with that in mind, we get this. And so neat fact, the boundary flux is a double integral computed over the interior. So this is kind of a modified Green's theorem, right? So our initial Green's theorem is that line integral, tangential line integral, is a double integral of Green's operator. Here what we're finding is that flux, namely normal, not tangential, but perpendicular, normal line integral, is a double integral of a different operator. Okay. By the way, anybody recognize that operator, perchance? Y'all remember this thing called divergence that we talked about a while ago? Lo and behold, eyebrow raiser. Hey, wow, what are the odds? Look at that. That's that same formula. Right. Okay, so I'm right now I'm just doing a little bit of foreshadowing. There is a point of view that we're going to talk about later. You can think of this as another kind of accumulation. Don't forget that where we got Green's theorem from is we looked at circulation, boundary circulation, and we did a chop it up, add it up, right? We made an accumulation argument. We showed that the little interior edges cancel, all that business to come up with Green's theorem. You can make an analogous argument to come up with this. And I don't want to make a reference to a name yet, but we'll do that soon. Okay. So moving along, let's do a three-dimensional version of this. Now, going back real quick, if you have a two-dimensional context, like a surface, like the surface of the Earth, right? Then you have curves, and you can talk about a fluid moving across the curve inside of that plane, inside of R2. Okay. If you are in 3 dimensions, as we are here, right? 3-dimensional context. Fluid crossing a curve, that's not really right. I mean, what defines the one side versus the other side of a curve in space? It's not a thing, right? But you can talk about a surface. And if you have a fluid flowing along, you can talk about how much of the stuff of that fluid is flowing through the surface, from one side of the surface to the other side of the surface. And it's really analogous to the two-dimensional notion of flux that we talked about. Specifically, it is, I don't care about this part, right? To whatever extent fluid is flowing along the surface, it's it's not flowing through the surface, it's flowing along the surface, right? Maybe our surface is a net, right? And we've got a net down there in the ocean, and the ocean current is pushing water through the net. Well, if the water, here's your net, right? If the water, to whatever extent it's flowing perpendicular to the surface, that's what we want to keep track of. That's how we're going to catch fish, right? Is by fish being pulled by the current through the net, therefore into the net, right? If the current is going that way, then all we're going to do is make some fish curious, right? The fish will be like here, and they're cruising along. It's like, oh, hey, look, there's a net over there. Weird. And then they just keep going, right? Right? So it's the through part that we're interested in, not the along part. So we throw away the through part. We throw away the along part. We look at the through part. Right? It's the component of the vector field in the normal direction. More component in the normal direction, more flux, more fish. Right? And likewise, and again, I think a pretty natural appeal. More area, bigger net, more fish. Yeah, pretty intuitive, pretty satisfying. Okay. So we likewise again. So components in the normal direction. Remember that unit normal vector is a unit vector. So component is a dot product. So okay. All right. So two big assumptions that go into this calculation. One is we assume that our net is flat. Right. I mean, we're assuming it's flat because we're using this single normal vector. If there is one normal vector defining the perpendicular direction, then that means that this is a flat surface. Okay. The other thing we're assuming is that the vector field is constant, right? I didn't really draw that, but I think that's clear how we're using that in the calculation. We're assuming that it's the same vector field all the way across. So what if that's not true? What if we have a curved surface? Something like that. And what if our vector field is doing different things? Maybe the vector field is like that, and but then it does some weird, stuff like this here. Right. So in some parts, the fluid is flowing through the surface kind of in one direction, and other parts the fluid's flowing sort of the other way. It's flowing not from the one side to the other side, but from the other side to the one side. It's just doing different things in different places. Right? So we can't use the formula on the previous page. You can't just take F dot N. That's which N? There's lots of N's. Right? Which F? There's lots of F's. So problem. So, no surprise. Chop it up, add it up. Okay, so we look at little pieces, chop up the domain. On each little piece, this is an easy problem. That little piece is approximately flat. The vector field might not be exactly constant there, but it's, look, it's a pretty small piece, so that its ability to, it might be something pretty different way over there, right? But over this short distances, it's probably pretty much constant. Right. So on each little piece, we have existing formulas. So let me draw that again. So on each piece, we can compute the flux through the piece. And if you want to then know the total over the entire surface, then you're just going to add up all of those little pieces of flux. Details we got to fill in, of course, right? But does everybody see the big picture strategy? Everybody good? Let me pause for a second, see if anyone has any questions. Okay. All righty. Okay, so lots to deal with, lots of little details to worry about here. For one thing, we're going to be adding up over a curved surface, and this curved surface, there's a lot of things I don't like about it. Not least of which is that it's dimensionally awkward. It's a two-dimensional thing in a three-dimensional world. And good news, we've already dealt with that problem, right? Our strategy for dealing with things that are dimensionally awkward is to parameterize them, right? View it as an image of something more desirable, like a rectangle in the plane, right? and then take the integral that we have on the right-hand side in this highly undesirable domain and just pull back through the parameterization. Right? So the pullback through the parameterization is going to turn an integral on the ugly purple domain and turn it into an integral on this lovely little yellow domain, which we like much more. Okay, so that is something we've already done. And not only have we talked about this strategy and used it in a different context, we've actually developed most of the actual tools that we need to adapt to this situation. So let me just remind you what we have. So we made this argument. There was this capital N vector that we came up with, right? It was now in the different context of trying to compute a scalar surface integral. Maybe we're computing the mass on this surface. It was the magnitude of this capital N that we needed. That was our stretching factor. So we're not looking at the same thing here, but nevertheless, anyway, let me just remind you, we have this thing called capital N, xu cross xv, as previously argued. Now we also have this idea of the unit vector pointing in that direction, so our little n, and I want to remind y'all, sorry for the notational inconsistency, but here and henceforth, little n is a unit vector. And I know that back in chapter 12, we didn't do it that way. Back in chapter 12, little n was, hey, whatever normal vector to the plane you feel like, whatever. Any length, it doesn't matter. Right? And so, not anymore. Now, little n is a unit vector. Okay. All right. But this is what I like to call on the large scale, on the, maybe you'd call it the finite scale. All of these are things that are, I'm going to say big, right? Now I'm going to talk about on the differential scale, by which I just mean all of these objects are differentials. So again, I remind you, don't think infinitesimal. That's not really a thing, right? But these are all differential things. So specifically, we were interested in computing a little piece of area. That little piece of area we call ds, and it's a differential amount of area. Right? We did so by looking at its edge vectors, which you remember we computed were xu du and xv dv. Right? Okay. And we came up with this formula that, excuse me, here's our stretching factor. The stretching factor magnitude of capital N, that was the thing that allows you to compute that ds by arguing how much it is a stretching out of the area that we have in the UV plane, namely du dv. Okay, so all that's old news. Okay, if you're a little rusty on some of those things, maybe go back and polish up on those bits. Okay, so here's the new thing I want to talk about. I want to talk about this vector here that I'm going to call the ds vector. We have not talked about that before. This is a new thing. And here's my definition of it. ds, it's, as shown above, it's these two things, which, now I owe you an explanation. If I'm going to define something to be two things, two different formulas, those had better be the same, right? So let me try to argue now why it is that these two things are the same. Let's see, let me do this with the pencil. Why is this equal to this? And the reason why is because they're both equal to the same thing, and here's what they are both equal to. They're both equal to little n times capital N magnitude times du dv. And how do I know that these are both equal to that? Well, that is clearly capital N, and du dv is du dv. So this little thing that I created up there is clearly equal to the left side, right? And this is ds, as previously noted, and little n is little n. So this is a little bit of kind of algebraic shuffling. It's a neat little observation there. So a nice punchline then is that these two things are equal, and being as these two things are equal, I can define something to equal to both of them. And again, my ds vector that I have drawn there is equal to these things. Okay. And you could reasonably ask, why would I be interested in such an object? Right, fair point. And that's going to come up momentarily. Okay. Alrighty. So that being said, well, here, let me go ahead and say a quick word about why we care about this thing. And I'm going to say more in a second. But this vector, this ds vector, is kind of the surface analog of the dx vector. Y'all remember the dx vector when we were doing vector line integrals? And what I like about the dx vector is the dx vector tells you everything you could possibly want to know about a little piece of curve. The direction that the dx vector points, well, that's the direction that the curve is going. The magnitude of the dx vector, well, that's the length of the little piece of curve. So the dx vector is kind of the all-encompassing everything you want to know about a little piece of curve. Well, likewise, the ds vector here is everything you might want to know about this piece of surface. Right? So the magnitude of ds is this piece of area. It's the area of the piece of surface that we're talking about. How do I know its magnitude is that? Well, because the magnitude of ds is the magnitude of little n ds. Little n's magnitude is 1, so the magnitude is ds, which is what we wanted it to be. Yeah. What direction does this ds vector point? Well, the direction that it points, well, it's the direction of the unit normal vector, which is telling me then the orientation of that piece of surface. Right? The unit normal vector is by being perpendicular to the surface, telling you how the surface is oriented in space. Okay, so it's a very natural object, this ds vector. Has all these nice properties. Okay, all right, so now reminder, what are we doing with all this? Here was our big strategy. We're going to look at each little piece of the surface. We're going to compute the flux through that little piece of surface. That's easy. It's little, right? It's itty bitty. It's approximately flat. The vector field's approximately constant. We have an existing formula for flux on a little bitty flat piece of surface. Then we're going to add up over the entire surface. So writing that down, here it is. On each little piece of surface, f dot n ds. And that's our existing formula. This is the component of the vector field in the appropriate direction. This is the area of that little piece of surface. Adding up over the entire surface gives me the total flux. So that's our big picture strategy. And now, while we're here, I observe, oh, hey, check it out. Look at that, in ds scalar. Well, that's our ds vector from the previous page. That's neato. Right? Different way to write the same thing. And then, don't forget, we have a different way to think about the ds vector. It's capital N du dv. So this gives us now 3 different ways to think about flux. On the one hand, you can think about it that way. What I like about this first point of view on flux is that it relates to the physical development, right? I mean, in other words, where did this formula for flux come from? Well, we made an argument about areas, and we made an argument about components in the normal direction, and you can see that in that calculation. Well, that's fantastic, right? That's very intuitively satisfying. So I like that notation for that reason. This is the notation the book uses, mostly. Okay. I like this notation, too. This is, and y'all are going to like this one. Because that's the one that you can compute from the parameterization. There's your plug and chug notation. Right? And, I mean, come on, that's handy, right? I mean, that's something we need. We're going to need to be able to compute these things, and that's the way in, right? You parameterize your surface, and having parameterized, notice how do I compute this in? Well, in is, I take the cross product of, let's see, it's xu and xv. What is xu? Xu is a partial derivative of the parameterization. So this comes directly from the parameterization. du dv, those are the parameters in your parameterization here. This is a du dv integral. This is the pullback integral. This is what you plug and chug with. So that's nice. Don't underappreciate this one in the middle. For one thing, it requires the fewest pen strokes. That's nice. Right? It's a very compact notation. And it's worth something. I really also like the fact, and y'all know I've talked about this kind of thing before, just like with the dx notation for vector line integrals, I like the fact that we have a single differential that's telling you everything that you need to know about the piece of the domain, right? What I have circled in green there, that's domain stuff in this expression. And then I have an entirely separate integrand, right? And having a clearly defined, what part of this expression is from the domain, what part of this expression is from the integrand, I think that's natural. I just think it's a natural way to think about things. Okay. So, of course, all that's in, these other notations. It's just that it's a little unclear, arguably, in these others. For example, there's a kind of an illusion here. It almost kind of looks like this is your integrand. And, look, it's the integrand for the pullback. Yeah, true. Right? But some of what's in there comes from the orientation of the domain. Likewise here. That looks like the integrand, but some of what's in there is not independent of the surface. Some of what's in there is coming from the surface itself. The surface dictates ds, but also dictates that little n. Okay. All right. So enough of that. Okay. Another quick pause. We have examples coming up. Is everybody on board with the development? Okay. Right. Okay. So I want to give you all a quick word of warning. It's an easy landmine to step on, but I don't want you all to step on. Let me segue into this by talking about a curve. Suppose I asked you to compute a line integral of a vector field along this curve, right? So this is C. I'm going to do a line integral on C f dot dx. Okay. That question, as I have it posed there, is unclear. Because I haven't told you which direction to go along C, right? So the line integral, the vector line integral, is very importantly wrapped up in, well, which way are we going? If we're going this way, we're going to get one answer, but if I go the other direction, I get not the same answer. Well, the negative of the answer, but importantly, not the same answer, right? Okay. So how does this come up in our calculations? Well, and let's suppose I have my orientation set now. So now I have a well-defined question. I want to compute a line integral along this curve oriented as indicated. When I parameterize the curve, you can't just parameterize whichever way you feel like. I've got to parameterize the right way. Right? I mean, if you parameterize it backwards, you're not going to get the right answer. In fact, you're going to get the exact negative of the right answer, right? So I think that's pretty believable. Now, where does that come from? Well, it comes from the fact that your parameterization, in this picture here, your parameterization gives you a velocity vector, looking at a given point here. And your velocity vector then tells you your unit tangent vector, t, that defines the orientation, right? So ultimately, it's in the algebra that your parameterization is going to give you an orientation. So when I say you have to parameterize the right way, you have to parameterize in such a way that the resulting unit tangent vector is right. Yeah. Okay. All right, so how do we ensure that? I mean, how do we think about this in the case of line integrals? Well, in the case of line integrals, the way we think about this is, parameterize it the right way. Don't parameterize it backwards. I mean, when you parameterize something, you're thinking of position on the curve as a function of time. So think of time causing you to move the direction you're supposed to move. It's intuitive in how you make your parameterization to, of course, parameterize it the correct way. Or we know that one of our tricks, and we talked about this back in section 15.2, another alternative is you could just parameterize backwards and then multiply by -1, right? That also works and is totally fine. Okay. But whether you've done it right or wrong is pretty clear. Okay, so the same thing happens with surface integrals. Your parameterization, when you parameterize a surface, that tells you what your capital N vector is, and implicitly, therefore, you are assigning an orientation to your surface, right? So let me draw this a picture of this. If you have a surface, here's a surface. When you parameterize, green. If you parameterize, that parameterization gives you a capital N vector. Maybe let's say capital N is like that, right? Which therefore gives you a unit normal vector, aka an orientation, little n, right? Well, what if that's the wrong one? Right? What if, it could happen. I mean, what if the original surface was oriented that way? Well, you just messed up, right? And you're going to get a wrong answer. You're going to get an answer that's wrong by a minus sign. And it's tempting to say, okay, this just isn't a problem with line integrals. Why would it be a problem with surface integrals? The reason it's not a problem with line integrals is because when you're parameterizing a curve, it is, like we just discussed, intuitively clear that which way you're parameterizing. You can see that in how time progresses or something like that. Right? It is not clear when you're parameterizing a surface whether you're parameterizing it the right way or the wrong way. There is no notion of time to sort of hang your hat on intuitively. Right? So what we've got here is a sneaky little landmine situation, and lots of students mess this up. Lots of students will parameterize with no worry for whether they're parameterizing the right way because they're not aware that they're parameterizing one way or the other at all. They're just parameterizing. And then it turned out you parameterize it the wrong way, and then they're wrong by a minus sign. And you get, wrong answer. Okay. All right, so here's the resolution of this, the way this works out. When you are parameterizing, as you parameterize, don't worry about it. As you parameterize, however, is the most convenient. But then figure out what your orientation is. Look and see which way you oriented it. Ask, did you parameterize it the right way or did you parameterize it the wrong way? And if you parameterized it the right way, hey, cool, yay, keep going, it's fine, not a problem. If you didn't parameterize it the right way, you have two choices. You could reparameterize, or what I strongly advise instead, just say, oops, right there on your exam paper, say, whoops, wrong direction, wrong orientation, adding a -1 now, smiley face, and you're good, right? That's fine, right? All I need is to see some recognition that you realize, what are the odds? I parameterized backwards. Here's my minus sign to make it all good, which it does. A minus sign fixes it. Okay, so let's see how that plays out in this example. We're not going to get very far in this example, but we'll get part way. We want to compute a flux. Here. There's our formula for flux. Vector field is given. Surface is a long discussion here, but there's our surface. And, of course, we've got to parameterize that surface. Here's our parameterization of the surface. We were looking at the part of a certain given paraboloid that sits above the unit disk down here in the plane. I'm going to parameterize with the graph parameterization. If you don't remember the graph parameterization, flip on back to the appropriate section where we talked about this. And the big idea is if you have a graph, then z is already a function of x and y. So just make x and y, this is the big trick, just make your input variables, your parameters. And then Z is what it has to be, and lo and behold, you got yourself a parameterization. Okay, so graph parameterization. And with that in mind, here's your XU, here's your XV, here's your N. That's just plug and chug. Again, the parameterization dictates your capital N vector, and now we can look and see if we got this right or if we got this wrong. And notice this normal vector, it's pointing it's hard to say exactly what direction it's pointing, but to some extent, you can see right there it's pointing upward. It's maybe upward into that way, upward into the side, or upward into the, I don't know about the rest of it, but it's not downward in any sense. And look up here at our definition of our surface, right? Our surface is given oriented downward. So we inadvertently, no fault of our own, what do you expect? Nevertheless, we parameterized the wrong way. And so the fix, it's again a really easy fix, is you just say, whoops, here's my minus sign, and you move on. Is everybody good? Okay, this is a good natural stopping point. We'll pick up here on Monday. Y'all have a great weekend. See you later.